you can divide your periodic table into blocks that tell you where the electrons are sitting for each of the elements. Okay, so this part on the left here is called your S block. These 6 columns, sorry, on the right is called your P block. This block in the middle is called your D block. And these ones down here, these ones actually extend out this way, by the way, just as a revision of module 1, yeah? Those last 2 columns actually extend out from that middle block. But it's just really long, so they separate it out. And this one down here is your F block. So as you go across your periodic table, you can assign the electrons to each one of them. So each box will represent an electron that sits in a particular orbital, and then you assign an electron each time as you go across through each element. So each row in the periodic table represents an energy level. So this one here is going to be energy level 1, energy level 2, energy level 3. And then because there's S block and there's a P block in the first energy level, and S and P, and then when you get to energy level 4, there's S and there's D and then there's P, there are different orbitals that can exist in the same energy level. Okay, so that's the difference between the Bohr model and the Schrodinger model. The Bohr model just said, oh, energy level 1, 2, and 3, and then the Bohr model split it up into SP, D, and F, but each SP, D, and F exists inside of an energy level. So it's sort of combining the idea of the orbitals with the energy levels together. So when you are assigning SPDF notation, you need to know the labeling, so S block, D block, P block, and F block, and then you need to know that each row represents an energy level. So the way you do it is this hydrogen here, it's in row number 1 and it's in the S block. So the SPDF notation for hydrogen is going to be 1s, and because it's the first box, it's the first element, it only has 1 electron. So the SPDF notation for hydrogen is going to be 1s1. Okay, now one s orbital can fit maximum 2 electrons. That's why the S block, each time you go across it, it's only 2 columns. The P block can fit 6 electrons in total. That's why there's 1, 2, 3, 4, 5, 6 columns in the P block. So the first number 1 represents the energy level. The S tells me that I'm in the S block, and the 1 up the top is where I use to count my electrons. So 1s, so 1 electron in the 1s block. So as I go across each box, each element, I will add on 1 electron. And the reason that's the case is because right now I'm talking about neutral atoms. And in a neutral atom, the number of protons is equal to the number of electrons. That's why the positive and the negative charges cancel out. So hydrogen is my first element. It has 1 proton. That's how your periodic table is organized. Okay, so to repeat, the periodic table is organized in terms of numbers of protons. Hydrogen has 1 proton, it has 1 atomic number. And then helium has 2, and then so on, 3 and 4. And then when you have a neutral atom, the number of protons is equal to the number of electrons because the charges cancel out. That's what it means to be neutral. So in this case, when I am doing SPDF notation, I happen to start off at the very top left of my periodic table because that's where it starts, which means I'm in the S block and I'm in the first row. So that's going to be first row, S block. And because I have my first element, it has 1 proton, which means it also has 1 electron. So that's where the little 1 up the top comes from. So the first number is the row, the second letter is the orbital, the number at the top is my electron count. So for hydrogen, it's going to be 1s1. Now, helium gets put on the right-hand side simply because it's a noble gas, and so it gets grouped with the noble gases. However, technically helium is in the S block, yeah, because it's only the second electron. So it doesn't jump into the P block, it just happens to be positioned there because it gets grouped with your noble gases. So for helium, because it's a second element, it's going to be 1s2, okay? So second element, 2 protons, which means also 2 electrons to cancel it out. So the SPDF notation for hydrogen is 1s1, the SPDF notation for helium is 1s2. And then my P block doesn't actually start until the second row, yeah? So helium's in the P block, but it's actually with the 1s. It just happens to be put on that side. So the P block doesn't start until the second row. So then when I go into lithium, lithium is number 1, 2, 3. So in total, the SPDF notation for lithium is going to be 1s2, and then this one as well, 2s1. And then for beryllium, it's going to be 1s2, 2s2. And then when I jump over to boron, boron is now in my P block region. So when I go over here, it is going to be 1s2, 1s2, 2s2, 2p, because I'm in the second row in the P block, and it's the first one, it's going to be 1. So in total, notice how the numbers up the top represent the electrons in each orbital, which means when you add it all up, it should be the total number of electrons that you have, okay? So 2 in the 1s orbital, 2 in the 2s orbital, and then 1 in the 2p orbital, which means in total, boron has 5 electrons, which makes sense because boron has an atomic number of 5, so it needs 5 electrons to cancel out the positive charge in the nucleus. Can I get a thumbs up, guys? Is this jogging our memory of SPDF notation from Module 1? Good. Awesome. So let's apply that to the question that we saw earlier, yeah? The question earlier was asking us, what's the valence electrons for the O2 minus ion? Now, O2 minus, okay, is not a neutral atom. So the protons do not cancel out the electrons. In this case, because there's a 2 minus charge, that means that it's actually got 2 more electrons. Yeah, so when it's a 2 minus, when it's a negative charge, that means there's more electrons than protons. When there's a positive charge, that means there's more protons than electrons. Okay, so the positive charges went out. So what I'm going to do with O is, first of all, I'm going to get to oxygen, okay? But then because there's 2 extra electrons, I'm going to jump 2 places. So it's the oxygen atom, it just has the neon electron configuration. Okay, so if I have a 2 minus charge, I'm going to jump to the right 2. If I have a 2 positive charge, I'm going to jump to the left by 2. Because now the electron configuration doesn't match the neutral oxygen atom, it looks similar to the neon one. So when I go to do my SPDF notation for O2 minus, I don't stop at oxygen. I stop at neon now because there's a 2 minus charge. So what I'm going to do is I start off with my S block again. So I start off with 1s2. I go all the way through my 2s block. So it's going to be 2s2, and then I start my 2p block. So 1, 2, 3, 4. I don't stop at 4. I would stop at 4 if it was just a neutral oxygen atom, but I go into 5, 6. So that's the second row in the P block. So my O2 minus SPDF notation is 1s2, 2s2, 2p6.